Hi, my name is Lauren Ward, and I am here to present my research in modeling the evolution of interpolating microstructures in nano-layered metal composites. I would like to begin by thanking my sponsors, the online OREU program at Texas A&M University, the Center for Research Excellence on Dynamically Deformed Solids, supported by the Department of Energy, National Nuclear Security Administration, and the Texas A&M University High Performance Research Computing Center. I would also like to take the time to thank my collaborators, Dr. Michael J. Demkovich and Dr. Zerui Mao. I would like to begin by defining an NMC. An NMC is a nano-layered metal composite with layer thickness on the nanoscale. An example of this is shown to the left here in Figure 1. At this nanoscale, the layers are so thin that the interface between the layers begins to dominate the material's properties. Typical joining methods for these NMCs can alter their microstructure. Figure 2 here shows a microstructure disruption in a copper-vanadium nanolayer composite that was due to high processing temperatures. These microstructure disruptions can decrease the interface area between the NMCs. These changes thus alter the microstructure in undesirable ways. For this reason, I will be modeling a method of joining NMCs that hopefully produces an NMC with a structure that is as close as possible to that of a pure NMC. The models described in this work could provide a framework for future theoretical models of NMC joints. Finding a viable joining method for NMCs would aid in furthering the potential widespread technological use of nanostructured metals. The model setup used for the joining simulations that I performed consists of two nano-layered metal composites, labeled here as NMC number 1 on the left and NMC number 2 on the right. These layers are separated by a filler material, shown here in the center, that has an average composition of 50% of each of the two metals that make up these NMCs. These are distinguished here by blue and red. Hence, the filler material shown is made up of 50% blue and 50% red. Joining of these two NMC layers occurs through the decomposition or phase separation of the filler material. Thus, a moving front is created at the NMC filler boundary. This allows for the growth of the outside layers in toward the center of the filler. The goal is to determine if this joining method will result in a structure close to that of the original NMCs, as shown here in the bottom image. It is important to make sure that this result can be constantly reproduced, even when various parameters in the simulation are changed. Phase field modeling was employed to observe the changes in the structure of the NMCs during the decomposition of the filler material. For this reason, it is important to understand the basics of phase field modeling. Phase field modeling is a quantitative model that describes the microstructural evolution of materials. This structure for the NMCs being studied will be defined using a conserved value called the order parameter. This order parameter will be assigned a value of -1, 1, or 0 for the pure red phase, the pure blue phase, or the filler material, respectively. The evolution of this order parameter, C, is described by the Cahn-Hilliard model as shown. The simulation shown here is an example of a final model that will demonstrate the growth of these outside layers into the center of the filler material. I will be solving the aforementioned Cahn-Hilliard model using MOOSE software. MOOSE is a finite element code used to solve partial differential equations. The results obtained from running these simulations will then be visualized using an application for scientific data visualization called ParaView. With these visualizations, I will then be able to determine and observe how the microstructure evolves in relationship to the differing initial conditions that I have chosen, such as layer thickness, misalignment, and average composition of the original NMCs. I will be running both MOOSE software and ParaView through the High Performance Research Computing Center at Texas A&M University. To reiterate, the overall objective of this research is to create models that will allow me to determine if this joining method will provide predictable and stable final NMC structures. I began by varying parameters in the simulation in order to determine if this joining method would prove consistent. The first parameter that I changed was layer thickness. Layer thickness refers to the original thickness of the NMC layers. Shown in the left image is the model with the thicker NMC layers, and shown on the right is the model with the thinner original NMC layers. So, did the thickness of the original NMC layers affect the structural evolution during joining and the structure of the final NMC? In short, yes. The series of images here shows the presence or lack thereof of inclusions within the layers of the NMCs. If the NMC layers became too thick, the post-joining structure could contain defects in the form of trapped inclusions that are circled here. Since the layers of typical NMCs are so thin, though, these inclusions are able to escape, as they need not travel far to reach an interface boundary between NMC layers. Thus, the final structure resembles that of the original NMCs. This is a desirable result, as the hope is to be able to join NMCs and obtain a final structure close to that of pure nanolayered metal composites. The next parameters that I varied in order to determine the fitness of this joining method were the layer misalignment and the average composition of the original NMCs. Layer misalignment refers to the misalignment of the two NMCs before joining. The amount of misalignment is defined by the percentage of the layer thickness by which the layers are shifted compared to the model with complete alignment. Shown here on the left are the layers that are completely aligned before joining versus the model on the right with layers that are misaligned by half of their layer thickness before joining. Average composition, the other parameter that I varied, refers to the percentage of the blue and red material that are present in the original NMCs in comparison to the filler material, which is still 50% blue and 50% red. The left model here, shown on the bottom, is composed of 50% blue and 50% red, just like the filler material, whereas the NMCs in the right model are much higher in average blue composition than the filler, which is still 50-50. So, did the aforementioned parameters that I changed, such as layer misalignment and average composition, affect the evolution of the NMC structure? They both did, in fact. As shown in the chart to the left, increasing both the layer misalignment and the difference in average composition resulted in a curvature of the advancing front that was not present in the original model. This advancing front is shown at the boundary between the NMC and the filler. This curvature increased with increasing misalignment as well as increased with average blue composition. This is evidenced as you look at the pictures of the advancing front in the chart to the left. More importantly, did layer misalignment and average composition also affect the final NMC structure? They both did. Again, the chart to the right shows an increase in final layer thickness when you increase both the layer's misalignment and the average blue composition in comparison to the filler. While the thickness of the resulting layers is changed, the structure is otherwise consistent with that of the two original NMCs. Overall, the final resulting structure was consistent with the formation of a stable and predictable microstructure for joining NMCs. Based on these results, the joining method proposed in this research could be a viable method for joining NMCs in the future. There are other variables, though, that should of course be considered in order to contain a more comprehensive analysis of this joining method. For example, the free energy model used and the material mobility of the two materials making up the NMC should be varied and investigated to determine if they affect the resulting NMC structure. Overall, the proposed joining method proves to be a robust method for joining NMCs that provides consistent final NMC structures.